Yeah.
We are on YouTube now.
Do we start now? Okay.
Yes, we are ready. You can present.
Okay. Good afternoon, good evening, or good morning to everybody. We're going to start this session, and this is a double session with young researchers. And the first one is Denilson Menezes from the Universidade Federal Fluminense from Niterói, Brazil. And thank you very much for accepting to participate in this web seminar. And he's going to present a work on equilibria for generalized Boussinesq fluid chemical models with multiplicative controls. So let us start with him.
Okay, thank you. I would like to thank the organizers for the invitation. I will talk about equilibria for generalized Boussinesq fluid chemical model with multiplicative control. This is our ongoing work with Henrique Fernandes Cara, Juan Límaco, Diego Souza, and Yuri Tamisten. The outline, the presentation is the following. First, in the introduction, I will motivate the use of Pareto equilibria and Nash equilibria. After this, I present some properties for the control to state mapping. In the multi-objective single-player model, I will give some definitions, first-order open-matrix conditions and second-order conditions. In the end, in the multi-objective multiplayer model, I will present some definitions in general results, first-order open-matrix conditions, and second-order conditions. The model is the following, is a Boussinesq system type. We consider the dimension 2 or 3. The U is can be a velocity field of a fluid containing a chemical substance with concentration theta. We primarily want to act in the chemical substance, so we use this functional J2, and this functional acts in the velocity field as well. So we enter with the second functional J1, and we use Pareto equilibria to harmonize the possible conflict between them. In the Nash equilibria, we consider any agents, and they act like before. And we try to find a Nash equilibrium, and each player has this functional Ji given by this expression. If you assume these initial conditions, and if G is in L infinite of Q, and the control V W is in L infinite of Q, we can find our solution in this space and satisfy this weak formulation of the problem. And if the dimension is 2, we can find better space for the weak solution in this space. In this theorem, we can find a T star that if you take the time in this interval 0 for T star, the system has a unique strong solution, U pi and theta, with this regularity, and solve the system almost everywhere in Q. If the dimension is 2, we can conclude this for all time, positive time. So if we fix a time in the condition of the previous theorem, we can, for each data, find a solution in this space that we call by W. So we can define this mapping that take the control brings to the solution of the problem, the state. So this application, this mapping is well defined. Before I continue, I present the linearized system. that is the system, that we can find a weak solution in this space. And if you derive the controlled mapping, control to state mapping, we can find that the derivative is exactly the solution of our linearized system with these controls. Here is the definition of Pareto equilibria. We have a performance criteria JI, I from 1 to n. We call V star, W star Pareto equilibrium if the system, if it does not exist V tilde W tilde with these two properties. Intuitively, we say that if you decrease a value of some functional, other one has to increase. In our problem, we consider this performance criteria with the two functionals, J1 and J2, given by these expressions. And here is our first result. This result gives us a sufficient condition to find a Pareto equilibrium. If we have a performance criteria JI, I from 1 to n, this affirms that argument of the convex combination of JI is Pareto equilibrium from this criteria. So this gives us sufficient conditions, and now we try to find necessary conditions. Before continuing, I present the adjoint system of our linearized system that is given by this system, and we can find a weak solution in those space. Now we can derive our functional. We define J as a convex combination of J1 and J2, and take the derivative of J. We find this expression, and integrating by parts, we find this another expression that appears the state of our adjoint system. So from the previous results, if V star W star is a minimize of J, then it can be written as a projection of this pair on U, where U pi and theta is the state with this control, and Z, I and psi solve our adjoint system with this control and this terminal condition. Before continue, I present this other system that is exactly the derivative of our adjoint system. He has a weak solution that belongs to this space. It satisfies this inequality, where observe that these constants doesn't depend of alpha and beta. So calculating the second order derivative of J, we find this expression that can be rewritten of this way, and you have to estimate these four numbers, I1, I2, I3, I4. For the I1, we can use Holder inequality and use the effect of L infinite Z0 TV is included in L6 of Q. So this norm is less or equal to this. And we use that the norm of H in L3 is less or equal to the product of these two norms. So we can find this expression and put this together with previous calculations. We find this inequality and observe that if this constant is positive, we conclude that our functional is strictly convex. So in the next result, we consider this constant positive. So the functional has a unique minimum, and we conclude that the control is a Pareto equilibrium for J1 and J2, if and only if this unique and minimized of J. So this gives us a necessary and sufficient condition to parity equilibrium. Now in the Nash equilibria, we consider n agents. Each one has a functional Ji and a strategic profile of Vi or Wi, I from 1 to n. And our system, the system that we consider is this one. Before I continue, I present some notation. U will be the product of Uj, J from 1 to n. U minus I is the product of Uj without the set Ui. And A minus I is an element of U minus I. So here is the definition of Nash equilibria. If we have the criteria Ji, I from 1 to n, I star is a Nash equilibria if each component is the argument of Ji in the component I. And if I star is a Nash quasi-equilibria for this criteria, if this expression is greater than or equal to 0, where Ji is the derivative of Ji in the entry I, in the direction I. And here is the functional that we use in our problem. The strategy that given a strategy, we assume that each query has this functional Ji given by this expression. So we have this following results. As before, we can derive our functional, and the derivative is given by this expression, where here appears the state of our joint system. U pi and theta is the solution of my system with these controls. Zi pi I psi I is the solution of our joint system with this control and this terminal conditions. If we consider these constants greater than 0, we can obtain this result that Gi in the entry I is strictly convex. So, as before, we can conclude results like this. I star I is the projection on Ui of this pair, where here U star, P star, theta star is a solution of our system with these controls, and Z star I, pi star I, and psi star I is the solution of our joint system with this control and this terminal condition. And if we consider this vector V star I, W star I from 1 to n, Nash equilibria, then we can conclude that this vector in here solve this system, and the system is called by optimized system. For the last result, we need to assume some things. The first one is our set must be convex, contained in L infinite of Q, and closed in L2 of Q. And these two exceptions, that Ui is contained in a ball in L infinite of Q. And if you consider a sequence AN that converges to A, almost everywhere in Q, then the projection on U of AN converges to projection on U of A. So now I can present this result that affirms that this mapping admits a fixed point. And in the end, this fixed point is a Nash equilibrium for our system. Now we use the Schauder fixed point, so we have to show that lambda is compact. To this, we consider a sequence in U, and for the previous theorem, you can guarantee this convergence in here, strong convergence, and maybe redefining the sequence, we can these other convergences in strong in L1 of Q and a more severe in Q. And using our assumption A2, we can show that lambda of AN converges to AB. So, and using the assumption A1, all this norm in here is less than or equal to R. So this together with dominated convergence theorem, we can infer that lambda of AN converges strongly in L2 of Q. So this shows that our function is compact. Since it's continuous, and we can use the Child fixed point to conclude that it exists a fixed point, and this fixed point will be a Nash equilibria, and this finish proof in the presentation. Thank you.
Okay, thank you very much. Now we have time for some questions. If you want to formulate a question, or you can do it also through the chat, as you want. Is there any question, any comment? Okay, I have a question. Maybe it's technical, but have you looked at other boundary conditions on the velocity or on the temperature? I mean, is everything okay in this case?
We consider this condition or boundary conditions. So I don't know if I understand the question.
Yes, you have imposed Dirichlet condition on U and Neumann condition on theta.
In theta,
okay?
yes.
So is your argument restricted to this case, or can you use another, can you impose another conditions on U? Or theta?
We don't, in theta, like Dirichlet condition or Hobby condition, is we just, we can, with Dirichlet condition, we can have the same result. I think we begin with this Dirichlet condition, and after this we change to Neumann condition. But you can have the same results for existence units for the system with Dirichlet condition.
Okay. And another question or comment in the same spirit. Have you tried to formulate and solve a similar problem with multiplicative controls on the boundary?
No, we didn't try that. I don't know if we can find some result in this. Don't know. But we can try.
Okay.
Mm-hmm.
Okay, is there any other comment or question? Okay, if there is no other comment, we are going to pass to the second speaker. Thank you very much, Denilson, for your very interesting talk. And we are going to begin with the second speaker now, Mihai.
Okay,
Can
let
you
me try to share the screen.
Share your slides, please? Okay, thank you.
Just a second, let me try to make them full screen. Okay.
Maybe you can try. Okay, perfect. Okay, the second speaker is Mihai Nechita from INRIA Paris, okay, thank you. And the title of the talk is now Unique Continuation Problems and Stabilized Finite Element Methods. So.
Okay, thank you very much. And first of all, let me thank the organizers for inviting me. This is joint work with Eric Berman and Lauri Oksanen, who were my PhD supervisors at University College London. Now Lauri is at University of Helsinki, and I think he will be giving a talk in this seminar next week. So let me start with some brief context, mentioning the fact that the unique continuation principle is a fundamental one in the analysis of PDEs, and that quantitative unique continuation appears quite often. Sometimes it's called propagation of smallness, as we have seen last week in this seminar when Nicolas Burck gave a talk on propagation of smallness for the heat equation. These kind of problems are ill-posed, and solving them numerically needs regularization. And also there seems to be a need of numerical methods where the convergence rates are explicit in terms of the discretization parameter. So there is also an interplay between regularization and discretization, and we will try to explore that more. So first, let me start with an abstract formulation of a unique continuation problem. And for this, let's take some open bounded and connected sets in Rn and an elliptic operator, L. And the problem reads like this. Given the data f and u omega, we want to find a solution of the PDE Lu equals f in the whole domain, which satisfies this particular restriction, u equals u omega in small omega. So the data for this problem is represented by f and the restriction of u in omega. And we want to recover u everywhere, or in a subset B, as shown here in the picture. The difference between recovering u locally or globally is in terms of the stability. And we will only focus on the case in which we recover u in a subset B, so not everywhere. Okay, now this problem, as I said, is ill-posed, and I want to briefly recall that if we formulate this as inverting this linear operator, which contains the elliptic operator and its restriction, then this operator has a non-closed range, which means that its pseudo-inverse is discontinuous. So we have an unstable problem. In other words, there is no uniform stability constant C such that the norm of u in the whole domain is bounded by C times the norm of the data. So the norm of Lu in H-1 and the norm of u in H1. Now this can be proven, for example, by a variation of Hadamard's example, and making the connection that this unique continuation problem is very much related to the Cauchy problem, which reads as in the system of equations 2, where again we have the PDE in the whole domain, but now we have Dirichlet and Neumann data on a subpart of the boundary. Sometimes people call this problem unique continuation. They are very much related, but in this talk, I will just focus on the problem with interior data. So as I said, this problem is ill-posed, and our goal will first be to try to see what stability estimates could be written for this question, and then to try to use them for a numerical method. And I will start with a general stability estimate that we aim to obtain, as the one written here. So on the left, we have the L2 norm of the solution in this subset B. And on the right, we have a first term, which represents the data on the data region, and then the right-hand side of the PDE. It appears at an exponent kappa, which is in between 0 and 1. And then another term, which comes from the fact that in order to have such an estimate, we must assume an a priori bound or nu everywhere. So our task is first to try to explore a bit what happens with this stability constant in the case of some PDEs in which the physical parameters play an important role. So we will focus on the convection-diffusion operator, minus mu Laplace u plus beta dot gradient u, and on the Helmholtz equation with a positive wave number. The idea being to see how the stability constant depends on the Peclet number for the convection diffusion and on the wave number for the Helmholtz equation. The starting point for writing down a conditional stability estimate in our approach is a standard Carleman estimate, which is written here in a compact subset, where we take a function rho that has no critical points in there, and then we build an exponential weight function. And what we have here written is a standard form of a Carleman inequality, in which the Laplacian is on the right-hand side, and you see these exponential weights. This holds for some large parameters, alpha and tau. This one is a standard inequality, as I said, and can be used to write down a quantitative unique continuation estimate for the Laplacian. And starting from it, in a similar manner, we write it down for the convection diffusion operator, just by trying to inject in the right-hand side this extra first order term. So without going too much into the details, the rough idea is that by taking suitable weight functions, one can, and importantly, a large enough parameter tau, one can then use this inequality to arrive at a three-ball inequality. So here, the domains that I mentioned at the very beginning, the one in which we have data, the one where we want to reconstruct the solution, are now balls. That's why this is called the three-ball inequality. So let me just emphasize here that it turns out that the stability constant may depend exponentially on the ratio between beta and mu, so between the convection term and the diffusion term. And also, I would like to emphasize the fact that here there is no regularity restriction on beta. It can be in L infinity. So this is a typical three-ball inequality. We would like to use such an inequality on the numerical analysis side, but for this, we would prefer to have weaker norms on the right-hand side. And by this, I mean, for example, the term Lu, which is in L2 here, to be measured in h-1. So we would like to shift this inequality with a Sobolev index. And using some technical methods from pseudo-differential operators, one can just shift the Sobolev indices in the whole inequality, and the result would be like the first inequality written here on the top. So here we see how the reconstruction in the ball B2 in L2 omega depends on the data and the a priori bound. And again, the same exponential dependence is noticed. On the left-hand side, we can change the norm from L2 to H1 using an auxiliary well-posed problem, but this would require an additional regularity assumption on beta. So for the moment, this would be the kind of conditional stability estimate that would have the norms written in a suitable way for a finite element analysis. And I will show you later how this could be used in proving convergence rates for a finite element method for such problems. But first, let me move to the Helmholtz equation and discuss stability for unique continuation in this case. Here, again, it's written a stability estimate in stronger norms. And what's important to notice is that in this case, if there are no assumptions on the geometry of the problem, then the stability constant could again blow up exponentially in the wave number. We've shown that it grows faster than any polynomial rate if there are lines that intersect the target region without intersecting the data region. And a recent preprint by Berger and Malinikova shows that for the Helmholtz equation, such kind of three-ball inequalities must have the stability constant blowing up exponentially in the wave number. In their paper, it's the L infinity, the maximum norms are used. So without any geometric assumptions, the stability constant might blow up exponentially. But under a certain convexity assumption, one can prove that actually the stability constant is independent of the wave number. As previously, our goal would also be to weaken the norms in the right-hand side to make them suitable for finite elements. So this would be the convexity assumption that I mentioned for the Helmholtz equation, which roughly means that one must assume data in a region like this gray one, omega, and the solution should be continued inside the convex hole of the data region. If this geometric setting is assumed, then the stability constant behaves nicely in the wave number. And for this, there are also previous results, many of them. I would just mention maybe one of the early ones by Khrushchev and Isakov, in which they have proven this conditional stability estimate. So here we have the norm for the data again is a stronger one. And this is called an increased stability estimate because the last term here, as k grows, this one would decrease. So one would roughly recover a kind of Lipschitz stability for this problem. Our goal is now to see what can be obtained for weaker norms. And for this, just a rough argument could be to consider a plane wave like this, u equals e to the ik dot x. and to rescale the H1 norm in terms of the L2 norm. So the rescaling would bring another power of k. And now the corresponding inequality could be the one at the bottom. So here we see that now we would have a stronger dependence on the wave number k. And the norms would be the ones that we want for numerical analysis. So this could be what we could expect from the previous results. However, a similar analysis starting from the Carleman estimate and then using some pseudo-differential techniques leads us to the stability estimate written in this lemma. So again, here we assume the convex geometry setting, and we would have that the L2 norm of u in B is less or equal than e to the power of alpha, where e is measuring the data, times the L2 norm everywhere raised to the power of 1 minus alpha. So here the constant, C, the stability constant, is uniform in terms of the wave number. So this would be a conditional stability estimate that we will make use of later on. Now, let me try to move to the second part of the talk, which will be focused on numerical analysis. So how to use the conditional stability estimates that we have seen on the numerical side in order to prove some convergence for some numerical methods. And the focus will be on finite element methods, and in particular on stabilized finite element methods. So let me first briefly mention a few words about stabilized finite element methods. And let me start with well-posed convection diffusion problems. So here we have a convection diffusion equation in a domain, and homogeneous Dirichlet boundary conditions are imposed. And we are now in the setting, in the convection dominated setting. So mu is strictly smaller than beta. Now, standard methods give spurious oscillations, and the solution has layers which are hard to detect by standard methods. Different stabilization mechanisms have been devised for this sort of questions, and I've just indicated here two references, two review papers actually, one more recent and one a bit older, and there's a huge zoo of stabilizing methods that one could use. The one that we will focus on is continuous interior penalty, which I will briefly describe next. So now let's assume a discrete setting in which we have a triangulation of our domain into some finite elements, and we consider the simple space of piecewise affine functions, and the weak form of the PDE, we define it through this bilinear form A in the standard way. Now, the idea of stabilization is to the weak formulation of our problem, which would be A UHVH equals F of VH, to add this extra term. And I call this the stabilization, the continuous interior penalty stabilization term, which is defined in the following way, basically penalizing the jumps of the gradient on the interior faces. And it's also, it also contains a scaling in the mesh size parameter H. So this, interior penalty stabilization is quite old, actually, from the 70s, but in the last 15 years, it has seen a sort of revival, and it was explored in different contexts. So now we will try to see how this would work if we want to approach the unique continuation problem from a numerical point of view. And for this, I will present a discretise first and then a regularise approach. So we are still at the discrete setting, and I will formulate a discrete Lagrangian which contains three terms. The first one in red, which is the data fitting term. So here capital U is the restriction of U plus possibly some noise. In our analysis, we will measure this data fitting term with an L2 norm that could be scaled. Then we have the PD constraint. So we introduce a Lagrange multiplier ZH. And then we have the extra stabilization or regularization terms, which for the moment, I will leave them quite abstract. We will see them later on. So this would be the discrete regularized Lagrangian. And the discrete solution now is UH, which is the approximation of the solution we want to recover, plus this Lagrange multiplier ZH. And writing the optimality conditions, the finite element method would look like the following discrete system. And such a discrete system, depending on how we choose the stabilizer, can be proven to have a unique solution. Its condition number can be studied, and then convergence can be proven. So I would roughly want to indicate some heuristics for how to choose the regularization. So here I'm again writing the finite element method, and let's notice that if the terms in blue would go to 0 as the mesh size goes to 0, then hand waving we would recover the original weak formulation of our unique continuation problem. So the stabilizers must satisfy certain conditions. First of all, they must be strong enough such that the discrete system has a unique solution. But as I've mentioned, they must be weak enough and converge to 0 in the right manner. This is what we call a weakly consistent. And now let me start with how the stabilizers could look like, or what one option for the stabilizers could be for the Helmholtz equation. So here we considered the data fitting term, just measuring the error in the L2 norm. Then we have the PD constraint, and then we have the stabilizer S, which acts on the primal variable U, which just penalizes the jumps of the gradient of the normal gradient on the interior faces. And then we have another term coming from the first order term in the Helmholtz equation. And then another stabilizer S star, which acts on this adjoint variable ZH, which will just be the H1 product. So the L2 product of the gradients. And for this system, the idea is that we can plug into the PD the error U minus UH into the stability estimate for the PD, which would read like the first equation here on the top. And now one would need to bound the residual, which can be done using the stabilization and the data fitting terms that we have considered. So without going into very much details, one can prove that that the stabilizing terms and the data fitting terms, which are measured in this triple norm, converge at an optimal rate for our piecewise fine approximation. And the residual can then be bounded by this triple norm terms. So at the end of the day, we would obtain an error estimate, which looks like the one written in this theorem, in which you see that the error, we have h converges as h to the power of alpha, and then we have a dependence on k, and then we have the L2 norm everywhere scaled by k squared, the H2 norm everywhere, and the noise which kicks in at a negative power of h. So this would be the error estimate for the finite element method. The convergence order alpha is exactly the one coming from the conditional stability estimate. So it is the same Euler exponent. And the dependence on k on the wave number is explicit. And let me show some numerical examples for this. I will show something for the following domains. On the left, we have a convex setting. So data is given in the gray region, and we do unique continuation upwards. In the middle, we have data again given in the gray region, and then the target region is the one above it. And then we have the example of two disks. So we have one convex direction and two non-convex ones. And for a homogeneous solution, we see that indeed geometry plays a fundamental role. So here on the left, we see the absolute errors for the convex direction. So quite a good approximation. And on the right, we see much higher errors for the non-convex direction, in which data was given in the centered disk. And if we increase the wave number, we see that the non-convex direction is feeling that way more severely than the convex one. And another solution that I will show is this Gaussian bump. So this is a sort of a natural solution for the Helmholtz equation because it doesn't depend on the wave number. So the dependence of the wave number is just taken into account into the right-hand side. But here the function, this function concentrates on this top boundary, and we will see what happens when data is given on the lower boundary. So on the left, we have the convex case, and on the right, we have the non-convex case in which data is given in a rectangle which touches this lower boundary. Again, we see the big difference between convex and non-convex. And in terms of convergence, here is a plot of the convergence rates. And we notice that the convergence order is sublinear as expected, and we see the right kind of convergence for the stabilizing terms, and also for the norm of the Lagrange multiplier. And in the non-convex case, because the stability constant now depends on the wave number, the errors are higher, but we still recover the expected convergence orders. And in terms of perturbations, recall that we had a h to the -1, which was multiplied with the size of the noise. So if the noise is of the order of the mesh size, the amplitude of the noise, then we do see some effect on the convergence plot. But for a smaller noise, order h squared, for example, there's no effect on the convergence plot. And now for the convection diffusion equation. the same methodology is applied, but now different different stabilizers are chosen. So here we are choosing the Lagrange multiplier in the same finite element space. Last time I forgot to mention, we chose the Lagrange multiplier ZH in a finite element space, which was the intersection of VH with H10. So functions that vanish on the boundary. In this case, we just took the same piecewise defined finite element space, which means that now in the stabilizing operators, some boundary terms will appear. So in this case, we take again the L2 norm to measure the data fitting term, and we scale it with some coefficients that depend on the physical parameters and the mesh size h. The primal stabilizer is again the continuous interior penalty one, so penalizing the jumps of the gradients across the interior faces, and we scale this again with some coefficients. And then the dual stabilizer is now enhanced, so we still have the H1 term, so the product of the gradient, but we also add the same jump operator and a boundary term. And again, one can prove that the discrete system has a unique solution, and in this case, we've also studied the condition number, which is bounded by h to the power of -4 and is independent on the physical parameters. So a standard finite element method would have a condition number that's bounded by h to the power of -2. So this is worse, as we expect, but it's independent on the physical parameters. And a similar technique, which is plugging in the approximation error into the conditional stability estimate, and then bounding the residual by the stabilizing and data terms, would lead to the error estimate that's written here below. So again, we recover the same convergence order, kappa here, as the Hurler exponent from the continuous level. And in this case, the dependence, the exponential dependence on the Peclet number just translates from the continuous to the discrete level. Again, an intermediate step is to bound the stabilizing and the data terms in an optimal way. So here, the optimal order would be h to the power of 3/2 for convection diffusion. And we obtain the same kind of scaling in terms of noise and the mesh size. I will show some numerical examples when diffusion dominates. So let me mention that this analysis is in the diffusion dominated regime. And the results that I will present here also. So here we have the two domains, the data domain small omega and the target region B above it. And on the right, we have a vector field with a divergence of 200. So this would be a non-coercive convection field for convection diffusion, where usually the divergence is assumed to be less or equal to 0 to have well-posedness. And we just want to exemplify that this sort of vector fields can be dealt with. So here we have a solution that is quadratic in X, quadratic in Y, with L2 norm, with a unit L2 norm on the big domain omega, and we see the convergence plots in the H1 norm, in the L2 norm, and in stabilizing norms, and they match the theoretical ones. So they are the convergence order is in between 0 and 1. So on the left we have the plot for a simple convection field, just constant in the x direction, and on the right the results for the convection field that I showed earlier. So we see that the errors are higher, but we still obtain sublinear convergence, even though the rate is slower this time. So here the diffusion coefficient was taken to be 1, and this is clearly a diffusion-dominated setting. Now, what happens if we look at the error plot? So in the diffusion-dominated case, when data is given inside in the centered disk, we see how the errors propagate towards the boundary. So this is what happens in the diffusion-dominated case. For a simple convection field, just unitary in the x direction. And now we will try to see what happens if we try to transition towards the convection-dominated case, and I will decrease the diffusion coefficient. So here we have two plots. On the left, we have the diffusion coefficient being 10 to the minus 2, the same solution, the same convective field, and we start to see the stronger effect of convection. So if we look at the previous plot, the approximation, the errors somehow propagate similarly in all directions, but here we start to see a better resolution from the data region across the characteristics that go through it. And we also notice a difference between downstream regions, so the ones to the right here, and upstream regions, the ones to the left. So we see that the error behaves more wildly on the upstream region than on the downstream region. And then if we so this is a sort of intermediate regime where convection is stronger, but it's not fully convection dominated. And now if we go to the fully convection dominated regime, we see that we can get very good errors on this strip downstream and upstream of the data region. However, in the perpendicular direction, the errors increase very fast. So this suggests that in the convection dominated case, a different kind of analysis would be suitable, where just because the stability constants would blow up exponentially in the Peclet number, one might not have a hope of having a good approximation in all directions, and should rather focus on obtaining better error estimates across the data region, both upstream and downstream. And for this, the numerical method stays almost identically the same, just with a stronger penalty in the data term. However, the approach is totally different. So we no longer use conditional stability estimates, and we rather use standard techniques from convection-dominated well-posed problems, where we focus on choosing a weight function and looking at weighted error estimates in local regions. And this would be a short sketch of the data region in gray and the stability region in which we might obtain a very good approximation. This one is hatched. And to not keep things too long, I would skip the details of choosing the weight functions. And I would rather show you the kind of error estimates that we obtain. So like the one here at the bottom, where we have the error in this stability region, which converges as h to the power of 3/2, which would be the optimal convergence rate, even for a well-posed problem when stabilized finite element methods are used. Even though there is this 1/2 gap, in practice we sometimes see the quadratic convergence, but in theory, as in the well-posed case, it's the convergence order is just 3/2. And in the upstream case, as I mentioned, there is a more complicated behavior in this intermediate regime in which the convergence order is reduced, but when convection fully kicks in, then we recover the same convergence order. So in this intermediate regime, we would have linear convergence and a stronger impact of noise, while in the fully convection-dominated regime, we will recover the 3/2 convergence order, and noise would be affected by h to the power of -1/2. So to conclude the talk, this was about unique continuation for two PDEs in which the physical parameters play an important role, and the focus on the continuum level was to come up with conditional stability estimates that were explicit in the physical parameters and with norms that are suitable for finite element analysis. And for this, the starting point was represented by Carleman estimates, and then the norms were shifted using some technical arguments. And on the numerical side of things, the approach was to discretize first the problem and then regularize on the discrete level using methodology already known from stabilized finite element methods. And I've just shown one possible option for the discrete stabilizers based on interior penalty, so penalizing the jumps of the gradient across the interior faces. The error estimates that we obtained are explicit in the physical parameters, and the convergence rates, they reflect the continuum stability of the problem. So when we use this sort of Hölder stability estimates, we rediscover the same convergence order, and in the case of convection-dominated problems, locally we obtain the convergence order that would appear in a well-posed problem. And with this, I think I will end.
Well, thank you. I think Enrique hasn't put his microphone back. Enrique, we cannot hear you. So, is there any question?
Yeah, so can I ask a question, Silvan?
Yes, of course. Go ahead.
So,
Yes,
Mihai,
excuse me, I have been,
okay.
I've been out. Enrique.
Here, Enrique Sva, second, thanking to Enrique first. So, Mihai, thank you for your talk. So, please tell me whether, of course, there are details there, I mean, that are, refined and need to be carefully checked. But so is your idea something like the following? So, I mean, is like the classical a posteriori, the idea of a posteriori analysis in which you see the solution of the numerical problem as a perturbed solution of the PDE with a reminder that you have to absorb through Carleman inequalities in some sense?
In a way, yes. In a way, yes. Yes. So the kind of error estimates that we obtain have this posteriori nature, indeed. Yes.
But you can, but so then if that is the case, could you do something similar for instance, just the classical P1 finite element method?
So you mean without any stabilizing terms?
Yes. So the question will be, because for instance, for the P1 finite element method, which is, I mean, in a very symmetric grid, is very similar to the finite differences. So we know that you can expect only unique continuation for low frequency solutions, right? So this is
so
something
and also
right.
yeah.
So I don't remember exactly where, but we wrote that a few years ago. But at high frequencies, the unique continuation fails. But in some sense, I mean, the way we understood that when we did it was that it's not so much related to the numerical scheme, but rather to the fact that out of the numerical solutions, you have to remove the high frequency ones, right? Of course, I mean, I understand your point. You can also dump numerically these high frequencies, adding some more viscosity or so, right? But going back to the classical finite element method, will your methodology lead to
I think a pure non-stabilizing method with this approach wouldn't work. Because first of all, the discrete problem might just be ill-posed, and then yes, and then without stabilization, we are in the situation that you mentioned of a discrete unique continuation, which is a sort of in some cases just a dead end.
Okay. Thank you, Mihai.
Thanks for the question.
Is there another question? Another comment, another question? Monsieur Puel, tu dis quelque chose?
Hello. In your three balls inequality, at the end, at least the last ones were obtained with the convex assumption.
Yes, for the Helmholtz, yes.
Okay.
Maybe I can go to the slide. Let me just.
Yeah, this one.
Yes. So these are in the convex setting.
The question is for the numerical estimates. Do you assume also the convex geometry assumption or not?
So let me try to go to the numerical examples again. So for example here, or let me actually go to the computational domains. So we tested in different settings, convex and non-convex ones, just to see if we can notice the effect of.
I understand that, but for the theoretical.
Yes, of course. Yes.
Error estimate, for the error estimate.
Yes, so for the error estimate here, the geometric setting is assumed to be the convex one. Okay. So that stability constant is the one that is being used.
Okay. Which means that when you apply that, when you apply to the non-convex set, it's not valid. You cannot.
Yes. So in the non-convex one, you can apply let's say a three-ball inequality, but with the constant depending exponentially on the wave number. Okay. So if you just fix a certain wave number, then you can still recover the same let's say sublinear convergence, but with worse stability constant, which would mean higher errors and maybe not such a clear convergence behavior to observe.
Okay, thank you.
Thank you.
Okay, thank you. Any other question? I have a question regarding the three-ball inequality you have used. Have you explored the geometry properties of the sets little omega and b, and the dependence of constant with respect to these sets? I mean, for different little omega, different b, how is the dependence of the constant?
Yeah, so let me try to, maybe I can go to one of these stability estimates. So let's say something like this. So in the case of actual three-ball inequality, so where the sets are actually balls, then it is known, for example, how the Euler exponent depends on the radii of the ball. So there is a dependence just on the ratio of those radii. The idea being that if you, for example, just reduce the data region up to a point, then this data term will just be 1. So you will and this kappa will actually be 0. So you will just end up with a trivial estimate, which would be rather useless. So this would be about kappa, how it depends on. So this is known for three balls and Laplace, let's say. And then the distance to the boundary, that's also an important thing, because if you want to estimate the solution everywhere, then this sort of Hölder estimate is no longer valid, but rather a logarithmic kind of estimate, as in the Cauchy problem, would be valid. So this would be another point about the importance of the geometry, let's say. But I'm not sure if I answered your question. Or...
No, okay. No, but I meant apart from kappa, you have the stability constant C. I wonder if in the estimates that you are using, is there something more subtle regarding the dependence of this constant with respect to little omega and b? For a two-dimensional or three-dimensional problem, maybe it's not only the distance to the boundary, it's something more than this. I wonder.
Yep. So now I think what in the way that I've written it here, it is somehow implicit on that it will depend on, let's say, the radii of the balls, but I'm not sure what an explicit form would look like. Okay.
Well, is there any other question or comment? Otherwise, we are going to finish. Thank you very much for your talk. It has been very, very, very interesting and very well organized. Next week, we'll have another talk by Lauri Oksanen, I think. So I hope you will be there again. So thank you to everybody for your participation, and see you next week. Bye-bye.
Bye.
Thank you. Very nice.
Goodbye. Thank you. See you.
Bye.